Welcome to this Yaskawa e-learning video for the benefits of using the Yaskawa Matrix drive on fans and pumps. I'm Paul Avery. In this video, we will consider the financial and functional benefits of using a Z1000U Matrix drive on a fan or pump application. First, we will establish the advantages of using any standard variable frequency drive over running a fan or pump across the line with dampers or valves to adjust the performance of the application. Then we will compare how the Yaskawa Matrix drive compares to a standard variable frequency drive or even a VFD with an active front-end package. Finally, we will review the technology behind the Matrix drive that makes it so unique. Once we understand how the Matrix works, we can understand how both the eco mode function and the inherent regenerative capabilities can be beneficial to fan and pump applications. Our first job is to consider and evaluate the use of a variable frequency drive, or VFD, versus just running the fan or pump using an across-the-line starter. An across-the-line starter can only apply full voltage and 60 Hz frequency to the fan or pump motor. Any changes to pressure or flow will need to be made using either dampers or inlet guide vanes for fans, or valves for pumps. Conversely, the VFD can run the motor at whatever speed that the fan or pump system requires. Fans and pumps run by VFDs do not need the dampers or valves. The drive uses only the power needed to match the demand, and the energy saved can provide a return on the investment in less than 3 years. The first issue we will consider is the power factor of a fan or pump application when using either a VFD or an across-the-line starter. We will try to use a familiar visual aid to understand the ups and downs of power factor. Power factor essentially designates how efficient the system is utilizing power. The closer power factor is to unity, the more efficient the system is using power. It turns out that some of the current does not actually generate the motor torque that moves the air or water. Some of the current is used to create the magnetic fields in the motor, which is required for the motor to generate torque. This reactive current is necessary, but doesn't directly move the load. The aim is to minimize it. One way to think of power factor is that the apparent power pulled from the utility is partly real power, or power used by the load, and partly reactive power necessary to produce magnetic fields. The apparent power is defined as kilovolt amps, or kVA. The real power is defined as kilowatts, or kW, and the reactive power is defined as kilovolt amperes reactive, or kVARs. And now for our familiar visual aid. How and why reactive power, or kVARs, are a reality when considering how power is drawn by an induction motor or VFD can be thought of like pouring beer into a mug. To get the beer from the keg into our mug, we would prefer that most of the contents stay in their drinkable liquid state, but some of it will become a foam head. We do our best to limit the foam, but some amount of foam is inevitable. Equivalently, we would like all of the power drawn from the utility to go to driving the load, but unfortunately, some of the power is lost to reactive elements in our system. For some reason, that last slide made me thirsty. Anyway, let's put some numbers to this power factor discussion. First, let's consider a fully loaded variable torque application, like a fan or a pump, running near full speed. When a motor is running across the line, the power factor is reasonable, but the inductive nature of the motor does tend to lower the power factor. When we take the same fully loaded application and drive it with a VFD, the VFD corrects for the motor's effect on the power factor. The VFD will have its own effect on the power factor, but the trade-off is clearly in favor of using the VFD. During low loads, proportionally more current is being used for magnetic fields than for driving the load, so the power factor drops pretty drastically. However, with the VFD, the magnetic fields can be fed from the drive's DC bus, so from the point of view of the utility, there isn't quite such a drop in power factor. Our next comparison will be in system efficiency, which we already kind of tipped our hand about when we discussed the VFD's ability to automatically regulate speed to meet actual demand. If we want to compare the efficiency of using a VFD on a fan or pump versus running across the line, we need to look at the amount of energy used by each method across their realistic operational range. Our aid in this comparison is the set of affinity laws, which govern power usage for fan and pump loads. According to the affinity laws, if we drop the fan or pump speed by 10%, we actually drop the power used not by 10%, but by 27%. So the slower the fan or pump runs, the greater the energy dollars saved. Because the VFD has the ability to run the fan or pump only as fast as is necessary at any moment, it can afford great savings in operation versus the single-speed motor starter. Although use of an inlet guide vane on an across-the-line installation can achieve some energy savings as it reduces flow rates, it cannot match the much lower power usage afforded by the VFD being able to slow down the fan or pump. Let's take a look at an example that makes it easy to understand the savings you can unlock by running your fan or pump with a VFD instead of across the line. In this example, we will have two identical 5-horsepower fans. When the CFM, or cubic feet per minute of airflow required, is equal to one of the two fans running at full speed, then the across-the-line solution will only run the one fan, while leaving the other fan off. The energy usage is equal to the 5-horsepower motor. When both fans are run by VFDs, and the CFM demand is equal to one fan running at full speed, the option to achieve that flow by running both fans at half speed exists. By running each fan at half speed, you actually drop the power usage by a cube of the speed reduction, which leaves the power at 12.5% of rated power, or 1.25 horsepower. That yields a power savings of 75% while still achieving the system requirements. Our next face-off between VFD operation for fan and pumps versus across-the-line operation will be over control options. The features considered next will go directly to how easy it is to work with each technology. When it comes to control options and capabilities, it really is a one-sided battle. The across-the-line installation has to run at full speed, starts with full voltage, which is stressful for both the mechanical and the electrical systems. It has no keypad, and it won't talk on any network. Conversely, the VFD runs only as fast as is necessary and can self-regulate to match the system's flow or pressure needs. The VFD will soft start the fan or pump, which eliminates inrush current levels and is far less stressful on the mechanical portions of the installation, like fan belting and pump valves, which in turn lengthens their lifespans. A VFD has the ability through its keypad to give real-time information on everything from the speed to the pressure to the amp draw of the motor. This information provides peace of mind to the person in charge of making sure the pump or fan is performing optimally. Lastly, a VFD can easily be integrated into an automation network via option boards or hardwired I/O. Most data acquisition is a cinch when the VFD can report details of its status in real time over the network. The next step in evaluating the matrix drive on fan and pump applications is to compare the unique capabilities of the matrix drive versus a standard 6-pulse VFD. As we have stated, any standard AC VFD has the ability to regulate a fan or pump to only run at the speed that the system demands, thereby eliminating the need for dampers, vanes, or valves to regulate pressure or flow. By automatically regulating speed to maintain demand, the drive automatically optimizes the system's operating efficiency. The matrix can do all that as well, but offers some distinct advantages not possible with a standard VFD solution. Again, let's begin our comparison with a look at the expected power factor performance of each device. What makes a standard VFD have better power factor than an across-the-line motor is that the displacement power factor is so much better when a VFD is between the induction motor and the line. Now that our comparison involves drives in both cases, displacement power factor is not really a differential. This time the differential comes from how much current distortion is created. Standard VFDs draw nonlinear current. In other words, the current is not drawn in line with the voltage. The greater the current waveform differs from the voltage waveform, the larger the current distortion. The true downside of the harmonics created by this distortion is that they also cause extra heating in the cables and devices that are supplying the VFD with power, without any real benefit. In the left-hand figure for the matrix drives, you can see that both the displacement power factor is very good and the current distortion is very minimal. Since we have brought up the topic of harmonics, let's try to give them a conceptual definition. Harmonics are, in a simple sense, just multiples of some fundamental. Since we are speaking of AC current, then harmonics are sine waves with frequencies that are some multiple of the fundamental frequency. In the graphic on this slide, the fundamental current frequency is 60 Hz. Also depicted are representations of the 3rd, 5th, 7th, and 9th harmonic of a 60 Hz fundamental waveform. Of course, standard VFDs and matrix drives are not the only choices when it comes to users concerned with mitigating harmonics and improving power factor. Let's compare the matrix to not only the standard VFD, but we will also add performance information for a VFD with an added DC bus reactor and also a VFD with a multi-pulse front end. Only by adding extra equipment, such as DC bus reactors or the special transformer and second rectifier bridge of a multi-pulse VFD, can we begin to eliminate the harmonics and improve the power factor. But even in those cases, we are still not reaching the harmonic mitigation and power factor improvements offered by a standard matrix drive. To minimize the harmonic currents at the input of the drive, you need the matrix drive. The matrix drive can operate at full load with less than 5% total harmonic current distortion. Even an 18-pulse VFD won't necessarily meet 5% total harmonic current distortion at its input. Our next comparison will be to compare the operational efficiency of a Yaskawa matrix drive versus a VFD with a multi-pulse front end. Here's an example of two 75 horsepower configurations, one an 18-pulse and the other the matrix drive. Both are operating on a variable torque load. You can see they both perform well at rated load. Still, the matrix drive is at least 3% more efficient at rated power. At lighter loads, the 18-pulse drive's efficiency suffers greatly. The matrix drive is still 94% efficient at 40% speed, while the 18-pulse has dropped down to 82% efficiency. That is a 12% reduction in efficiency. That is money out of your pocket. Let's continue our comparison of the matrix drive and a standard VFD by considering their control options. Frankly, there is no difference when it comes to control and convenience. As a matter of fact, our matrix drives feature the same keypad, the same programming menus, and the same option cards as our standard drive products. If you know how to use and operate a standard Yaskawa fan and pump drive, you can seamlessly transition to using a matrix drive. The final section of our matrix drive discussion will cover two more matrix-only functions that put it in another class above standard VFDs. We will present how the eco mode function and the inherent regenerative capabilities can be beneficial to fan and pump applications. To truly understand how the eco mode and regenerative capabilities work, we must first understand the technology behind the matrix drive. The power section of the matrix is dominated by 9 bidirectional switches. The 9 switches are required because we need to be able to connect any of the 3 input phases to any of the 3 output phases. Also included in the power section is an input filter. The input filter is necessary to filter out the pulse width modulation of any regenerated power going back to the power supply. Let's take a closer look at the 9 switches. By using the bidirectional switches, the matrix drive has the ability to allow motoring or regenerative power flow. Now we can discuss the eco mode. Sometimes the benefits of being able to vary the speed of the fan or pump are lost because the application is demanding full speed or near full speed operation. During these conditions, it would be nice if we could just open and close some contactors in order to shunt around the drive, bypassing it, and run offline power. The matrix drive takes the concept of a bypass and integrates it into its control to automatically switch back and forth between drive control and operating the motor using line power directly. This is called eco mode. Using the eco mode function, the matrix can be programmed so that when it is running the fan or pump near line frequency, it will simply pass the incoming sine wave power through untouched. When the application no longer needs to run up near line frequency, the matrix will transition back to PWM switching and run the fan or pump at whatever speed the application calls for. Eco mode eliminates audible motor noise, drive switching losses, and high frequency noise like common mode and differential mode noise. Going into eco mode can improve drive efficiency by 19% on average. Our final benefit of the matrix drive is the inherent regenerative operation of the matrix drive technology. Most fan and pump applications don't require motor braking during their normal operation. However, high inertia fans can cause a VFD to trip on an overvoltage condition as it reaches set speed. The inertia of the fan will want to keep the motor accelerating, so the VFD will need to deal with the regenerated energy. This causes a regenerative condition which sends energy from the motor back to the VFD, causing the overvoltage fault. The matrix drive with its bidirectional switches will automatically send this regenerative energy back to the line for tripless operation. The matrix is also helpful to prevent OV faults caused by large supply fans overhauling smaller return fans. Everything necessary for regeneration is built right into the Matrix. Thanks for joining me to cover the benefits of using Yaskawa's Matrix drive on fan and pump applications. If you have any questions about Yaskawa products or technology, please feel free to visit our website at www.yaskawa.com or send us an email at training@yaskawa.com. Thank you.